So my name is Scott Parker. I'm the lead for the performance engineering team at the Argonne Leadership Computing Facility. I used to work for Pete when he was the head of the facility. Today I'm going to talk a little bit about the architecture on one of our newest machines, the Cray XC40 that has the Knights Landing processors. The system's name is Theta. Before I get too far in the weeds on Theta, I just want to give you a quick overview of the other machines we have at Argonne. So in addition to Theta, we have our older Blue Gene Q platform, the largest of which is Mira. Mira is a 10 petaflop machine with 50,000 nodes. And one thing you'll notice, if you compare Mira and Theta, they're both about the same in terms of raw computing power, but Theta has far fewer nodes. And so what we're seeing here is that this particular architecture packs a lot more computing onto fewer nodes than the Blue Gene does. And in a lot of ways, they're very similar. They have same peak flop rate, roughly about the same amount of memory. There's a lot of architectural differences, but there's a lot of architectural similarities too. They're both many core platforms. They run different instruction sets, but a lot of the programming aspects of getting performance from them you'll find will be the same. In addition to Mira, we have some other Blue Gene Q platforms that are basically identical, just smaller scale. So we have Cetus, Vesta. I'm not really going to go into those. Finally, the last one we have is a much smaller scale system, Cooley. It's 126 nodes, and this is really meant for post-processing your large simulation data that's coming off of either Mira or Theta. It has GPUs on it for doing visualization. So those are, I think all of you have access to all these machines, or at least most of these machines while you're here. And I think the two more interesting ones would be to play around with Theta since it's the newest, and really Mira or Cetus, because they've been very good machines, and they'll give you a lot of understanding of where we're going with the many core architectures. And you can see the differences between those machines and the newer platform Theta. And just to put this in context, so Theta is a bit of a shift for Argonne. Argonne ALCF facility has been around since 2006. Back in the day, we started with, this is about the same time that the Blue Gene line of computers first came into existence. They actually showed up around 2004. We got our first little tiny Blue Gene back in, this is a Blue Gene L 2005. And since then, all the way up till the delivery of Theta, we've been on Blue Gene. So we started with the Blue Gene L. We went to the Blue Gene P, which was 160,000 cores, half petaflop. And then in 2012, we got Mira at 10 petaflops, also a Blue Gene. So this is the third generation of Blue Gene now. And basically, right after that, we started thinking about our next machine. And IBM at the time, despite Blue Gene being, I think, probably one of the most successful HPC platforms that I've seen, IBM basically didn't see a business case for continuing it. So they discontinued their work on Blue Gene. They decided not to do next generation. So we had to think about where we wanted to go next. And the answer was over to the Xeon Phi, because it has a lot of similarities. It's basically following this sort of many core architectural track that you see, and that's really what Argonne has sort of invested in. If you go to another facility like Oak Ridge, you'll see that they're on the accelerator GPU architecture line. And so between us and Oak Ridge, we're basically providing sort of two architectural flavors for folks to work on, and you can kind of pick which one works best for you between the two facilities. So what is Theta then? Well, Theta is actually sort of a precursor to our next big machine that's coming in the next few years. This machine called Aurora will also be an Intel Xeon Phi machine, but it'll be a future generation. This is going to take a little while longer than we sort of ideally would like to have come, given that Mira went into production in 2012. So in the interim, we got a machine. We got Theta, with the idea that it sort of will give us some good computing power to work on over the next few years, and it also gives us an opportunity to get familiar with the architecture and for our users to move their applications from Mira to the new Xeon Phi architecture. And I will say that that's not an overly difficult task for most codes and most people, but it is a change, so we wanted to give people time to spin up. So let's take a look at Theta. As I mentioned, Cray, this is a Cray system. It's coming from, it's Cray XC40. It has about 3,600 compute nodes and 200,000 some odd cores. And like I mentioned before, it's 10 petaflop peak performance. It's been around for about a year. We've had it up and running in production for about 6 months. but the first hardware sort of showed up at the end of last year. It is the Xeon Phi Knights Landing processor. The particular model number is 7230, and I'll explain why that's sort of relevant on the next slide. This particular one has 64 cores, and this is the frequencies that it runs at. Most important one is this one. This is your vector AVX frequency, and you'll see why that sort of ultimately determines for most codes what sort of performance, if you've optimized your code well, you're eventually going to be able to get. Memory-wise, we have about 736 terabytes total memory. Now, this is an interesting thing. This is an area where we see some real architectural innovation on Theta and also going forward. In the past, all our machines basically ran some form of off-socket DDR, right? So it's just a bunch of little chips soldered onto the board that were connected to the processor, and more or less commodity memory. Sort of the best performing version of it you can get, but still commodity. The issue with that is, these processors are getting so fast and consume data so quickly and do calculations that the memory subsystem can't keep up. And so we've had to see, the architects have had to sort of work around that problem. And their solution on this generation machines is to have two forms of memory. One is the traditional DDR. So we have DDR4 2400. So we have a lot of it, 192 gigabytes per node. But we also have this 16 gigabytes of MCD RAM. And I'll talk a little bit more about what that is. But this is basically fast memory. So it's sort of, we have two forms of memory now in the system. And this is a bit of a programming challenge for these machines. Fortunately, Intel has provided a lot of ways you can use this, so you have a lot of options, and some of them are relatively painless, but may not give you the best performance. And there's more painful options, or more interesting options, I should say, that you can get better performance with. So a supercomputer wouldn't really be super if it was just a regular connection of nodes connected by regular old Ethernet. So a big part of these machines is the network. I'm not going to talk a lot about the network, but towards the end of the talk, I'll give you a little sense of what it is. In this case, this is coming from Cray, so it's Cray ARIES Interconnect. This is technology they've had on a few of their other machines, a few previous generations. It's in the Dragonfly topology. So when you look at networks, you sort of want to think about two things. What are the underlying, hardware implementation? So in this case, it's the ARIES NIC and the ARIES router. And then how are these things all wired together in the topology? And there's a bunch of flavors for that. Fat trees, and Blue Gene is 4.5D torus, and in this case, this machine is a Dragonfly. And I'll give you a picture of that later on. And we have to store our data, so we have a large file system consisting of 10 petabytes currently. That will probably grow as the machine gets used more and the file system starts to fill up. Okay, so let's take a look at the pieces that go into Theta. As I mentioned, we have the KNL. So this is, each node is a single socket of KNL core. It's got its DDR memory and its in-package memory. Intel will spec it out, and our variety is coming in, I think the top variety at the time is coming in at 2.66 teraflops per socket. What Cray's done is they've taken 4 of these sockets along with an ARIES chip that has the router and the NICs on it, and put them onto a single board. So you have 4 of these sockets plus an ARIES switch on a compute blade, and that gives you about 10 teraflops of compute power. And you won't really see this aspect as a programmer, but this is an important aspect of the design of systems and how you package these and get them into a reasonably compact system that you can still cool and deploy and not have it take up acres of floor space. So while as computer scientists or engineers or scientists, we don't worry about this part, it's a very important part of the supercomputing design, and it dictates a lot of what we actually end up with in the final system. So Cray takes 16 of these blades, which packs them into what they call a chassis. So you can see it's very densely packed. This system is liquid cooled. Most of the newer computing systems have to be liquid cooled. In the old days, it was just big blowers blowing air through racks of these machines. They consume so much power, they generate so much heat that's just not viable anymore. In Cray's case, it's sort of a hybrid of liquid and air cooled, where they have basically, if you look at the whole system, so 3 of these chassis go into a cabinet. So if you walked into the machine room, you would see just rows of these big black cabinets lined up. And on one side, they more or less have a big radiator where cold water is pumped through, and then there's a blower that blows air through these chassis and extracts the heat. And then on the other side, that air is vented into the room. So it's not quite liquid cooled in the way the Blue Gene Q was, where on the Blue Gene Q, the liquid actually went to the processor itself and cooled it directly. So it's a bit of a hybrid design. So on Theta, we have these cabinets. They're about half a petaflop each. And we have 20 of them, so that gets us up to 10 teraflops, 10 petaflops, sorry. And that gives us a total of the 3,600 nodes. We have 9,600 switches. And we end up with what we call 10 groups in the Dragonfly topology. And that's something I'll talk a little bit more about later on. All right, so what is the Knights Landing processor? This is sort of a marketing slide that I borrowed from Intel, but I think it gives a nice overview of what is it that makes the Knight Landing sort of distinct from the previous generation, if anybody's ever run on it, the Knights Corner Xeon Phi, and also Intel's other mainstream product lines, the Xeon processors. So if you've ever run on the Knights Corner architecture, you probably know that it wasn't a standalone chip. It wasn't a standalone processor. It was a coprocessor or an accelerator attached to a regular Xeon. That's not the case for the Knights Landing. So the Knights Landing is its own basically standalone processor. It can boot an OS. It can run independently. I have a little server sitting in my office that's just looks like a regular computing box that's running. The only processor in it is a Knights Landing processor. So this gives it sort of like an independent existence. You don't need to have other processors there and you don't have to worry about moving data back and forth between that across a PCI bus and the main processor. It is compatible with the mainstream Xeon line, so it runs the same instruction set that the Xeon runs. Now, there's a few caveats to that, and I'll go into those details a little further as we go into the talk. But basically, you could take your code or even a binary from another platform that you've run on and just dump it onto Theta, and it should run. I wouldn't recommend doing that. You're not going to get the best performance, but it will work. The architecture is new, so Intel's had this KNC around for a while, but they've sort of, if you've used that, they've fundamentally re-architected the chip. I mean, there's really very little architectural similarity between that chip and the KNL. So, that's reflected in the performance, which comes in at 3x higher. They've added to the vector density, so that basically the chip is doing longer vectors, as you see down here. They have this new AVX512 instruction set architecture where the vectors are 512 bits long now, which allows it to do more operations in one instruction. And that's where you get this performance that can top out over 3 teraflops per chip. And they've added some interesting architectural features like gather scatter, which lets you do memory operations to multiple disparate, sort of memory addresses that are scattered across the machine in one instruction. And these aren't things you necessarily would use directly, but the compiler knows how to make use of them. As I mentioned before, they've introduced this sort of hybrid memory arrangement where you have the fast memory and the slow memory. The other aspect of these chips is they've come up with a new on-die interconnect. And this is a big aspect of the design for these chips. Now that you have more and more cores on a processor, you have to get those cores talking efficiently to each other into the memory subsystem. So you have to start putting more and more resources into that interconnect that lies on the chip. And this is a new design for Intel, though they are taking this design and sort of incorporating details of it into the Xeon line. So there's a lot of sharing now between the Xeon and the KNL. And finally, this isn't something that's relevant for Theta, but you may see this on other machines that run KNL, is they've integrated the network, Intel's OmniPath fabric, right onto the processor die itself. So you don't have to buy a separate NIC if you're using KNL processors on an OmniPath fabric. OK, so let's take a look at the processor. This is sort of a high-level schematic view of the chip itself. So the chip has 8 billion transistors, so a lot of transistors. It's on Intel's latest process. This is their 14 nanometer process. And this is the basic architecture where around the perimeter you have scattered memory. So you have these MCD RAM fast memory. You have 8 stacks of them. And then on the sides you have a DDR memory. So this is your old school off-socket memory. And in the middle here, you have all these tiles. And these black lines are the mesh interconnect. So you have 36 tiles. Each tile contains 2 cores. And they're all connected by the mesh interconnect. And like I said, you have memory with 16 gigabytes total of the fast memory. And this fast memory, as I mentioned, it's noticeably faster than what you're going to see on the DDR. So you're going to get about 5 times the memory bandwidth from the on-package memory than you're going to see from the off-package DDR memory. But capacity is much different, 16 versus 384. And then down in here you have their OmniPath networking integrated onto the chip itself. I mentioned that Theta runs a specific variant of the Knights Landing, and Intel denotes them by SKUs. So our flavor is the 7230 flavor. If you run out at NERSC, they have a KNL machine there, Cray. They run a slightly different variant, the 7250. And really the big differences between these machines are the number of cores. Intel's announced, though I don't think they've released, at least I haven't seen one, the top line processor for this line of KNLs, which will come in at 72 cores. So you have a sort of choice running from 64 to 72 cores. And then the frequencies also vary a bit with the higher SKUs being a little faster. And you can see this reflected in the performance that you get. So there's about a 30% difference between the lowest variant and the top variant, with the top one coming in about 3.5 teraflops. And if you look at the power, you'll see most of them are consuming about 215 watts. This top level one is pulling an extra 30 watts. And this has become a big factor in HPC design, is ultimately one of the big constraints these days is power. So while it may not seem like a lot, this 30 watts here, you may not see a lot of these guys on a large HPC system, even though it's the fastest and arguably the best. That little bit of extra power may be something that dissuades people from actually deploying it at large scale. Okay, so regarding the processor, I want to take a kind of deeper dive into it, and I want to kind of start from the outside and dig my way in. So the first thing I want to look at is the mesh interconnect, because this is really what ties the whole system together. And as I said, as they put more and more cores onto a node, this interconnect becomes more and more of a design issue that they have to sort of figure out how to optimize. So in this case, what Intel has chosen to do is they've done a 2D mesh. So basically you have all your components are little blocks that lie on this grid, and then you have these roads or lanes that just run between them in the X and Y direction. And so the pieces that connect to them are these tiles. So the tiles have the processors and the caches and all the compute elements. So you'll see a whole bunch of them. There's up to 36 of these tiles. Around the edge you have the MCD RAM controllers, and off on the sides you have two DDR controllers. So each of these DDR controllers connects to 3 channels of DDR. And then finally you have the off-chip I/O, so this is things like PCIe. So if you want to communicate or move data around the chip, basically, if a tile wants something from memory, let's say this tile wants data from memory over here, it will send its data up along the y-axis, and then it'll turn and run over the x-axis until it gets to the memory that it wants to be at. And at each of these intersections, you have to arbitrate. So it's just like stoplights. If you have 2-lane, roads where you have oncoming traffic going both directions, someone has to decide who gets to go. So every time you make a turn, you have to wait your turn to sort of get back in the line. So it's sort of like joining an expressway in that sense. The whole node is cache coherent. That means if one of these processors over here updates a data value and then someone else goes to read it, they will see the same value, right? The one that you just wrote. So you don't have to worry about different processors seeing different views of the data. It's all cache coherent. And it uses this MESIF protocol that manages all that. So this is a standard protocol for cache coherency. And this design has become complex enough, and really getting an optimal has become challenging enough that Intel sort of punted and said, well, you know what, we don't know the best, the way to set this up in operation. And so we're going to give you options, and we're just going to let you choose how you want to run it. And so they've come up with these clustering modes. And with all these tiles and all these memory controllers scattered around things, you can imagine you can run into traffic jams on the die itself with, if all these tiles want to talk to this particular memory controller, they're not going to be able to do it. Or if all the tiles on this side want to talk to somebody on this DDR controller and vice versa, they're going to run into contention. And you can try to minimize that contention by putting the machine into different clustering modes. And there's actually quite a few of them, but the main ones that Intel has sort of put forward as options are the all-to-all, Quadrant, and Sub-NUMA. So all-to-all is basically this idea that there's 3 things that have to happen when you, there's 3 major steps in resolving a memory address. The tile generates, or the core generates the memory address that it wants. Since we have cache coherence on the chip itself, you have to check and see, well, does this address that I want here, is it living somewhere else in one of the caches on these other tiles. So you have to go and ask, and there's a directory that says, what is where, what is in the cache somewhere else on the chip. And that's actually distributed across the chip itself along with the caches. So that for every memory address, it would know who to go and ask. So in this case, this tile or this processor generates a memory address, and it turns out the guy that knows where that might be is living down here. So it has to send its request down to this tile. This tile says, oh, well, it's not in memory, it's not in cache, so you got to get it from memory. So that memory may be up here, and then that memory address gets resolved and sent back to the tile that generated it. So you can see you're kind of running around the whole chip in this all-to-all configuration, which could lead to congestion. So you can run the machine in this mode if you want, but most people would say, well, there's no advantage to doing that. There's better ways to do it. And one of the other modes that Intel has created, and these are all selectable at boot time, is this Quadrant mode, where what it does is it creates affinity between the cache directory and the memory that's holding the actual data address. So in this case, you're guaranteed that the guy that knows where the memory is in cache and the memory controller that's holding the data live in the same quadrant or same quarter of the chip. So in this case, you sort of minimize the amount of traveling that you do, at least keep it localized within 2 quadrants, the one you're in and the one that the memory and the cache directory live in. And so this is probably the one that most people run the chip in, and it is, I think probably the best option for most scenarios. But if you want to go a little bit further, you can try to minimize your cross traffic on the node by going and running in what they call Sub-NUMA clustering mode. Now in this case, the chip's going to look a little different when you boot it up. All previous cases, if you booted it up and just asked, the OS how many sockets are there or how many NUMA domains are there, it would just come back and say there's 1 NUMA domain. So the all-to-all and the clustering would just say that there's basically just everybody lives in one memory space. Everything, there's no preferential access or performance differences between touching any of the memory from any of the cores. If you put it in a Sub-NUMA clustering mode, what it's going to do is it's going to come up as 4 virtual sockets or 4 NUMA domains. So it's going to make it look like, from the OS perspective, like there's 4 sockets. And there really aren't. So you get the same performance that you would get otherwise, except in this case, it lets your program do things like set affinity between the tile that, let's say, malloc the memory and the cache directory that's holding the memory. So now you can keep all of your traffic confined to 1 quadrant. And so this limits the likelihood of that you'll have conflicts and congestion on the mesh. Yeah?
So does each one of those hops take 1 clock cycle? Or?
That's a good question. I would say at least 1 clock cycle, yeah. So you'll notice small differences. I haven't, it's fast enough that a memory address resolution is going to take you several hundred clock cycles. So an additional hop, even though it might cost you a little bit, is marginal in the overall cost of accessing memory. And I don't think I've played around with this a little bit, and in theory, if you're accessing this memory from this guy down here, it should be a little slower than accessing it from this guy. And I think that is true, but it's marginally different. So maybe a few percent in terms of memory bandwidth that you achieve. But yeah, it does cost you something. And so you're best off if you want to run it in this mode where you say maybe have 4 MPI ranks and then or more on a quadrant, you kind of minimize the number of hops that you might do. Yeah.
You mentioned Intel doesn't know really. Well, one of the reasons it did this is because it wants to give the programmer the choice of. Do you have any inclination or any experience in figuring out which way is it better for most of our codes to be run?
Yeah, actually, the quadrant mode works just fine. Like the difference in clustering modes in practice ends up to be pretty minimal unless you have sort of pathological case. So my advice would be you can play with it. It's kind of interesting to play with, but in practice, unless you're really going for that last 0.5% of performance, quadrant mode is fine. You might start with quadrant mode and then play around with the SNC4 mode. There's actually other modes that are variants of these. So if you go and look at the docs, there's another 6 or so modes that you could play with. But these are the main ones. And quadrant's really the one that you want to play with. And I mean, I think, yeah, I am unfairly characterizing Intel's approach, which is that, I think they looked at it and said, well, we can just let the programmer decide, right? They didn't bind you to one. The only thing that, as a programmer, it makes your life a little more difficult sometimes because you have all these options now. And in reality, those options don't make too big of a difference in practice, except for certain limiting cases. OK, so that's the mesh, and that's how everything gets tied together on the node. Let's now look at the sort of basic building block of the compute part, which is the tile. So the tile contains 2 cores, And each core has 2 vector units. And here they're sort of shown as sort of discrete blocks, but really they're so integrated into the core that if I was going to redraw this diagram, I would just include them in the core itself. But what they do share is a 1 megabyte L2 cache. So they don't have their own private L2. So they can fight over this. And you can see that in some cases where one core is knocking another core's data out of L2 and causing problems. And the last piece is this awkwardly named caching home agent. And this is really the guy that, I was talking about that distributed tag directory. This is the guy that keeps all that data. He keeps the L2 coherent. He manages the MESIF protocol. And he's the interface. So all the data that's coming on and off the core or the tile goes through the CHA. So this is the interface. This is the on-ramp, if you will, onto the mesh. And if you open up one of these cores, what you'll see inside is that sort of this architectural view where you have this Atom-based processor. So Atom is Intel's low power line of processors. And the particular flavor that they sort of built the KNL off of was the Silvermont. This was Intel's pitch at the cell phone market. And I think they've recently decided that they're not making enough money there. So they're not really pushing their Atom line in that market too heavily these days. But it's a very power efficient architecture. And in HPC these days, that's the critical piece. You want power efficiency. So if you look at what you get on this architecture, so you have so an instruction cache, so pretty much standard on every processor. This is where your instructions live until they're pulled into the pipeline. And so you have fetch and decode. So it pulls 2 instructions per cycle. So this architecture is limited to at most 2 wide or 2 instructions per cycle in the decode name and retire stage. So it pulls in 2 instructions, figures out what it's going to do with them, and then sends them off to the appropriate pipeline. So in this case, we have 2 vector pipelines, and these are out of order. So basically, there's 2 reservation stations here that can hold instructions, and they filter down through this pipeline. You get your results, and then that gets retired back into memory or registers wherever it needs to go. If you're not doing a floating point instruction or a vector integer vector instruction, you would go through the integer ALUs. So you have 2 integer ALUs here. So these do things like integer add, subtract, multiply, things like that, or bit rotations, things like that. And then you have 2 memory units that do fetch and load operations from memory. And they're connected to an L1 cache, so 32 kilobyte, 8-way associative L1 cache. So you can pull 2 64-byte vectors out of that per cycle and write 1 64-byte vector back. And the integer and the vector units are out of order. So that means that the processor has leeway to reorder the operations as long as you get the same answer. So like if it looks like one of them is going to stall on a memory reference or something, you can skip over that one and go on to the next one. So it can do its best to keep the processor busy. So at the execution stage, you have 6 wide execute. So you can actually have 6 instructions in flight through the pipelines, but ultimately, you're bottlenecked on the fetch and store back, so you can only ever get sort of sustained 2 instructions per cycle through the processor. In addition to the pipelines, the processor supports 4 hardware threads per core. So the hardware threads, they've been around for a while. The BlueGeneQ has something similar. There's 4 hardware threads on a BlueGeneQ processor. Intel calls these hyper threads. You've seen them on the Xeon probably. The idea here is that there's more hardware on the chip that allows up to 4 threads per core to sort of operate efficiently. So they each have their own register file. They each have their own state that's sort of saved in its own hardware. But they're all sharing the same compute pipeline. So one thread is capable of using all these compute pipelines. So having 1 thread per core, you can fully utilize the core. However, that's often not achievable in practice because you have memory stalls and things like that. So you may see an advantage to going to 2 threads per core or 4 threads per core if you're running on this machine. And this is very program dependent, so you want to experiment with this. But when you do run 4 threads per core, you're not going to get 4 times the performance because they're all trying to push their instructions through the same set of pipelines. So they all have to wait for each other's instructions to get out of the way. So you're only ever going to do 2 instructions per cycle. You could do that with 1 thread if it's really optimized, or maybe you need 4 threads to make that happen in practice, or even get close to that. And they share things like the caches and the TLB. So if you put 4 threads per core on a node, this 32 kilobyte L1 cache is now going to get chopped up, and effectively each one gets a quarter of it. So there's trade-offs to doing this. And depending on what your code does, you may or may not. But I would say if you're running on this architecture, it's good to experiment. Start with maybe 1 thread per core, then try 2 and 4, and see which one works best for you. on your code. I mentioned the instruction set on the KNL and that it's compatible with the x86 legacy instructions. So you can see here it supports SSE, AVX, AVX2, all the things that were on the previous Sandy Bridge, Haswell, Broadwell platforms. And this is really the first platform that's introduced the AVX 512. So these are 512-bit vector instructions, but it won't be the last one. So Intel's going to bring these over into their future Xeon platforms. They may already be on Skylake. I actually don't know if that's the case or not. But so code that you write for KNL and optimize for AVX 512 isn't sort of like, the only place that it can run is not on the KNL. It can run on the upcoming Xeons here too. And actually, they're going to kind of continue to expand this instruction set with further byte word, quad, double word. And I actually don't know exactly what these do. But Intel sort of parsed out their instruction set pieces and merged, labeled them and put them into groups so you can kind of see which processors will support which. And there's actually a couple that are specific, though somewhat obscure to the KNL, which is the prefetch for gather and scatter and the reciprocal square root estimates. So these instructions will only exist on the KNL, but they're things that typically the compiler would generate specifically, so you don't have to worry about it. But it may mean that your binary, if you took a binary from KNL that was using these instructions and put it on a Xeon, it may not run because it doesn't have these particular instructions. So let's take a look at what kind of performance you can actually get on Theta in terms of compute. So here we just took a simple DGEMM kernel from MKL. One thing, if you look at Intel's marketing slides, they'll tell you that the KNL on Theta can do something like 2.5 or 2.6 teraflops per second. That's actually really not true. They're using the fastest clock rate that you can get, or the main clock rate, 1.3 gigahertz per cycle. You can't do that when you're running the vector instructions. So when you run these AVX 512 vector instructions, the chip clocks down to 1.1 gigahertz per cycle. So after it sees a few of them, it says, oh, you're going to do a lot of vector operations. For power reasons, I'm going to slow this thing down. And so it does. And in that case, at 1.1 gigahertz, you can use two vector pipelines, each doing, for double precision, 8 operations, and they can do a floating point multiply add, which is a multiply and an add in one instruction, so that's 2 flops. So if you do the math, that comes out to about 2.25 teraflops. And if we run MKL, we get close to 2 teraflops, or about 86% of peak, which is about as well as you're going to do for any kind of kernel on just about any machine. And if you look at the performance you get, if we run it with using just 32 cores, we get about half the performance that we get, 32 threads here using 32 cores. We get about half the performance that we get using 64 threads and 64 cores. And if you start loading up with extra hyperthreads, you see that it doesn't really help because you're already maxing out the performance of the core with just 1 thread per core. So adding more threads doesn't get you anything. Yeah?
The 2 pipelines, 1 thread, use both pipelines?
Yeah. 1 thread can fire instructions through both vector pipelines, which is why you can get maximum, close to 86% of peak on a DGEMM with 1 thread. So there's a few wrinkles here. Like I said, where you're limited by the AVX frequency, not the 1.3 gigahertz that Intel quotes for this. There's a few corner cases where you actually won't even be able to get 2 instructions per cycle through. I won't go through that because really that happens fairly rarely. But if you find that you're achieving far less than what you expect, there are issues where you can fetch 16 bytes of instructions per cycle, and some instructions are 12 bytes long. So in some cases, you can only fetch 1 instruction per cycle. OK, so that's the processor. Now I want to step back again and take a look at the memory. So this is sort of a quick schematic of the memory. And here we have a core. It's connected to its L2. So if you load a memory address, it'll either find it in the L1 cache, it'll go up to the L2. If the L2 cache doesn't find it, this is where we get into this sort of novel memory architecture, where your address could be resolved in one of several places, any one of the 8 stacks of MCD RAM that are clustered around, or it can go into the DDR. And the real difference here is the bandwidth that you get. As I said before, you're getting much better bandwidth out of the in-package memory than you are out of the off-package DDR memory. However, you can't probably fit everything in your code into the in-package memory because it's limited to 16 gigabytes. So the trick is, how do you program this to use this well? And here you have, again, options. And so you can at boot time, you can decide, how do I want to use the in-package memory? And you have options of cached, flat, or hybrid. I would say most people have not yet played around with hybrid, and it's probably a corner case. So the 2 choices you have are cached or flat in practice. And the idea here is, if you set it in cache mode, your MCD RAM stops being memory and it becomes a cache. So it just becomes like a big L3 cache. You don't have any direct control of it. You don't see it. And essentially, any memory address runs from the CPU through the IPM cache or the MCD RAM cache. And if it's found there, great. It returns very quickly. If not, it just gets forwarded onto the DDR. And so this is sort of transparent. You don't have to do any code modifications to use it this way. If you get a lot of cache hits out of your MCD RAM in package memory, your code will run really fast. If you don't, it will run basically at this memory speed, which can be a lot slower. You have less memory because now your IPM is sort of duplicating what's in your DDR. So you give up 16 gigabytes of memory. And there's some bandwidth and latency implications that I'll show you on the next slide to doing that. So your performance, even if you're hitting in the cache all the time, can be worse than you get in flat mode. In flat mode, you say, well, you know what, I don't want the machine to try to cache things for me. I'm going to do it all myself. In that case, when you boot up, you'll see two memory pools. One address space, but with two sort of physical backings to it. So you'll have the lowest 192 gigabytes of memory will be the DDR, and the last 16 gigabytes of memory will be the in-package memory. So here you have to decide yourself what goes where. So you'll have to make those decisions. The upside is you get better bandwidth and latency. You have more addressable memory, but you're going to have to change your code. And if you don't like either of those two options, you can say, well, I want a mix. I want some of my fast memory as cache and some of it as directly manageable. So you can set, pick from a few ratios. And there's, if you're running in flat mode, there's some options or some libraries that you can use, JEMalloc, memkind, and pragmas that you can use to make those declarations of what goes where. And you can also use the NUMA CTL command, which will let you just put all of your data into one or the other sets of memory. And I mentioned there's some performance implications to these choices, and this is sort of an analysis of those performance trade-offs based on the stream benchmark. And basically what this boils down to is you get your best performance out of flat mode, where you get the 485 and the 88 gigabytes per second. We don't see much impact from the clustering modes. A single core can only drive 14 gigabytes per second of memory bandwidth, so if you're just running on one core, you're not even getting close to this. You need to use at least half the cores to max out the MCD RAM. But if you run in cache mode, what you'll see is that you get slower memory, performance out of the memory. And basically you give up about 25% of your memory bandwidth just from running in flat mode, cache mode, period. And this is related to it having to do an additional lookup in the cache to see if the data is there. So it has to do a read for every write. And that's why you get slow. Intel's sort of, another issue is there's these streaming store instructions that if you don't use them, you get even poorer performance even from the flat mode itself. So this is an optimization that if you know you're not going to reuse data, you can use streaming stores to write it. Yeah.
So a lot of things need to be chosen at boot time. Does it mean if I submit a job to Theta that the nodes can be booted based on JavaScript instructions?
Yes. Yeah, you can configure that now. We didn't used to, we had them sort of hard set up, but I think now you should be able to tweak them in the way you want. And finally, the last thing on memory I want to mention is the memory latency. So you can see that the cost or in cycles to accessing memory is a lot lower if you're in the lower caches, a lot higher if you go out to MCD RAM or DDR. And actually the DDRs, even though it's slower in bandwidth, it's a little faster in terms of latency. So if you're latency bound, you may want to run out of DDR. I'm going to skip over this slide, but this gives you sort of some insight into the cost of OPENMP overhead. And basically it's saying that since there's no last level cache, OPENMP overhead can be a little high in some scenarios. All right, and the last thing I want to go through is the Cray ARIES DRAGONFLY network. And this is sort of a very quick schematic overview of the network itself. So you have 4 nodes that are connected to an ARIES chip. So this is sort of the building blocks of the network. And then they can send data across the ARIES links at basically between 4 and 5 gigabytes per second per direction. So what happens in the ARIES the DRAGONFLY topology, how this is composed is you take these 4 nodes that are connected to a single ARIES and you put them in a grid of other sets of nodes in ARIES. That's 16 by 6, and then you have all-to-all connectivity. So basically each one of these little blocks has a direct link going to each of the other blocks in its row and in its column. So if it wants to talk to somebody and a message originates here and it's going over here, it just hops up to the ARIES, gets on the direct link to the next to that particular node, and then down into the processor. Or vice versa, if it's going up a column, it does the same thing. If it needs to go to another node, let's say one up here, it's going to have to make 2 hops, one over to this column and then up the column to the node that it wants to arrive at. So this makes what we call a group. So this 16 by 6 group has 384 nodes. And you have a lot of connectivity within a group. So there's a lot of bandwidth that you can drive. If everybody's talking to everybody, you can have a lot of messages in flight because there's a lot of links going between all these nodes. This is a group. Over here we have on Theta, we have 10 groups. Each of the groups is then connected all to all the other groups. So basically off of each one of these little boxes is a link that comes off and goes over to another box in another group. Now the problem is you don't have nearly as many links going to a given group. So you may have only 5 links going off from one group to another given other group. So there's a limited pipe going between any 2 groups. Now you have a lot of bandwidth going off to the collective set of groups. So often what you'll want is to see, you'll see that the default is to sort of scatter your job across many groups. So you have a lot of links connecting all the groups in your job together. And this just gives you some sense of the performance that you can get out of this. So this is OSU MPI benchmarks. And you can see here we're doing message rates and with message size. So you can send about 24 million messages per second. So this is how quickly you can send off if you're doing small 8-byte MPI messages. And this is the bandwidth you can get off of a node. So you see as you use more ranks, you can get better bandwidth, peaking out at about 12 gigabytes per second off the node for large messages. And this is the latency you see. So it basically boils all down to it costs you between 3 and 4 microseconds to send 1 byte to another node on the network. And finally, this is the MPI collective performance. We looked at a couple of them, ranging from 32 to 2048 nodes. And you'll see that like all reduce is slower than the other ones that we looked at, broadcast and gather, because all reduce has to do an operation, right? It's a reduction. So in this case, it's probably doing a sum. So you have to go to the processor and do the sum operation. So that pushes your latency up to a couple hundred microseconds. Otherwise, you know, it's relatively flat. So no matter how many nodes you use, the cost of doing a gather or a broadcast doesn't change too dramatically. Now, what's interesting is if you look at this and you talk to the MPI guys, they'll probably tell you that the broadcast should be faster than the gather. And this is an implementation aspect that Cray probably didn't get quite right in their MPI. So you can ask Bill Gropp or whoever's here, you know, why that is. But there's some interesting things. Finally, power efficiency. I'm not going to say too much here since I think I'm over my time. But basically, running 1 thread per core, more power. You can do more gigaflops per watt. So that's the most power efficient way to run. And MCDRAM is a lot more power efficient than DDR. So you get basically 1.6 gigabytes per second per watt versus 0.4. So in the future, expect to see a lot more MCDRAM as the prices come down versus DDR, just basically based on power, well, power and performance. It's a quick slide on comparisons of Theta and Mira. I'm not going to walk through it because I'm out of time, but if anybody has any final questions, I'll take them real quick.
So having dabbled in the Knight's Corner, the biggest change for me is the self-booting aspect. Is it even possible to run Knight's Landing as a coprocessor? Yeah, it actually is. I didn't mention it because it's sort of irrelevant to us, but you can get them packaged as a coprocessor. I've never seen any examples of people using it that way, but they are selling it in that form factor or that package. So it may be that people want to drop it in to, you know, replace a KNC or something like that. I think one of the big advantages to this is you don't have to do that. So I don't know that too many people would want to if they can avoid it. Any last questions? Yeah.
Is the compiler different from Intel?
Yes, we have the GNU. On Theta, we have GNU, we have LLVM, and we have Cray. So you have, plus Intel. So you have 4 different flavors to choose from.
Do you have any preferences?
I think the Intel, for most codes for vectorization, does the best. That's not true for every single case, but that's probably, you know, not looking at your code a priori, I'd say start with the Intel. But, you know, there's various, you know, different cases are handled better by different compilers, so you kind of have to experiment.